All right, guys. So we've seen the form of the steady state equation, or the equation that describes steady state enzyme kinetics, right? Um, Now the question is, you're studying an enzyme and you really need to know something about the properties of this basic enzyme. What's its Vmax? What's its Kcat? What does the Km look like? How good an enzyme is this at a given substrate concentration? So that, of course, leads us back to a theme that I've been repeating over and over again, is we collect some basic data, we plot that data in some way, and then we fit a model to that data, right? So how would you execute an experiment like this in terms of steady state enzyme kinetics? Well, with, of course, having some pure enzyme, you'd run a series of experiments, of course, right? So you run a series of experiments in which you would vary the concentration of the substrate, right? And then measure the initial rate, right? And then from that data set, you should get data as a function of time, right? And here we're measuring, the concentration of product, right? Remember, what we're thinking about here is the reaction. If you remember our basic scheme, E plus S goes to ES to E plus P. So our basic assay is going to be measuring for the appearance of our product, right? And most assays are going to be configured this way. Okay, so you do that, and you, again, like I said, you vary the concentration of S. What you're going to get, what you should get, if this is working correctly, is a series of curves that look, something like this. Say, you do a set of experiments, right? You're looking at the production of your product as a function of time, right? And you better get a family of straight lines that look something like this, right? Where, in this case, the going in this direction, the concentration of our substrate is increasing, right? And the slope of each one of these lines, right, is equal to the initial rate at that concentration of the substrate, right? So we would have, sort of a whole series of these, P02, P03, P04. So we're getting an initial rate measurement at a series of different substrate concentrations. And as I said, these better be straight lines, right? So if you did an experiment like this, right, and your curve did something like this, right, or started out like this, but then it started doing something like that, you've got a problem, right? There's something wrong with the way you're doing the assay. You're not under steady state conditions, so the steady state model doesn't apply, or there's some bigger problem. The assumptions of steady state enzyme kinetics begin with the idea that the production of substrate as a function of time is a constant. Basically, it's going to be linear, right? Okay. All right, so assuming that didn't happen, you got a set of data that looks something like this. The next thing you, of course, do would be to take those initial rate measurements, right, and do a second plot, right? You would now come down here, and as a function of the substrate concentration, take a look at your initial rate measurements, and you would plot these guys out, right? Maybe you have some noise here. Oops, get a little bit better here. And these would do something like this, right? And I'm trying to wing it this way. Probably should. Yeah, that's better, right? So now you would take this data, right? Of course, it better have a shape that looks something like that. Specifically, it better have a parabolic shape, because we know from the derivation we went through last time that assuming steady state kinetics apply, that we've done the experiment right, that we're looking at clean homogeneous enzyme, we don't have any other confounding effects, that the function that describes this dependence of the initial rate on the concentration of substrate is simply this K2 concentration of total enzyme, concentration of substrate, divided by, of course, the Km plus the concentration of substrate. Or written another way, V max times concentration of substrate over Km plus the concentration of substrate, where of course V max is just equal to that K2, or let me write that the way we'd started changing it, the so-called Kcat times the concentration of enzyme, total enzyme, right? Excuse me. Okay, so let's look at that again. There's some things, as we've seen with simple chemical kinetics, we talked about it with binding kinetics, that we can sort of estimate or get a feel for right off the bat, just from looking at this plot. And the first one, very much analogous to what we did before, is consider what happens if one sets that initial, that Michaelis equation equal to 1/2 V max, right? Equals, say, V max concentration of S divided by Km concentration of S. In other words, if our maximum rate up here was set, of course, by that asymptote, here, and if we came down here to this 1/2 Vmax point, right? What does that tell us about, right? So you can get that in principle by solving that basic equation that I just set up there, right? You cancel out the Vmax, of course, and you solve. What you find is that the concentration of S at 1/2 Vmax is just equal to the Km, right? That means that has to equal the Km, right? So kind of like we saw with binding data, like we saw with an exponential decay, looking at that half amplitude point tells you something characteristic, right? In the case of steady state enzyme kinetics, the concentration at that 1/2 Vmax point is equivalent to the Km. Now that also means something else if you think about it, right? It means we can think about this concentration axis in multiples of the Km, right? Because Km, if you remember that definition for Km, right? Just K minus 2, excuse me, good grief. Come on. K2 plus K minus 1 over K1, right? And if you remember, we had K1 here, K minus 1 here, K2 here, right? So if you think about the type of constants those are, of course, K2 is a unimolecular rate constant. K1 is a unimolecular rate constant, right? And K1 is a bimolecular rate constant, right? Well, that's kind of cool, because you think about that, that means the units up, the units up here have to be seconds to the minus 1, that numerator there, and this is molar -1 second to the -1, because remember, it's a bimolecular rate constant. Those cancel out. That means the units of Km are just concentration, say molar, right? And like I said, what this means is because the units of Km are molar, we can think about this substrate concentration axis in one of these Michaelis plots in units of Km, right? So we have Km here. Here we'd have like, this would be like 2 Km, 3 Km, 4 Km, right? Okay, that's actually kind of useful because that now puts a little more of a mathematical explanation on something we know has to be true up here at the top of this plot, which is this asymptote, right? We can look at that and say, well, that's where the enzymatic reaction is going at its maximum rate. So that's probably the Vmax. But if we think about what I just said here, in terms of thinking about this concentration axis in units of Km, what that also means is that when the concentration of the substrate gets much larger than the Km, right? Then under those conditions, the initial rate is equal to the Vmax, right? And you can see that if you even just look at this expression here. If the substrate concentration got much bigger than this, right? Then in that sum, in that ratio, this would then basically become insignificant. That and that would cancel out, and the V0 now equals the Vmax, right? Okay. So those are some really useful things you can read right off one of these plots. You can get an estimate of sort of what the Vmax is by looking at that asymptote. You can get a sense of the Km, right? But if you really, again, wanted to be quantitative about this, and usually when you're doing enzyme kinetics, you want to be quantitative, you're not just going to eyeball it off a plot. It gives you a good feel for it. It's a good technique to know. But you really want to do enzyme kinetics. You're doing something quantitative. You want to get the real numbers. And that, of course, means taking data like this, right? Importing it into an appropriate data analysis package, again, like HugoPro, and then doing the thing we've been talking about, setting up the appropriate fitting function and fitting your data to that model, right? Okay. But as we've seen, again, I've shown you this at least a couple times before with kinetics and with binding data. In an era before the existence of these nonlinear regression packages and inexpensive and powerful computers, people couldn't analyze their data this way. And so there is a whole family of linear transforms that people used of enzymatic steady state kinetic data, steady state enzyme data, that would let them use slopes and intercepts to try and get at these parameters, right? And again, like I pointed out before, in the modern era, most people doing this kind of thing, if they want to do quantitative about getting these parameters, wouldn't use these linear transforms so much anymore, right? There are still some good reasons for doing it, kind of in the same way we talked about transforming binding data from that standard plot, hyperbolic plot, into that titration binding plot, that log, that's function of log of concentration, where you get that sigmoid. And that transformation tells you something about how the quality of your data, how well it fits what you think is going on, just visually by inspecting it. These linear transforms provide a similar double check because they exaggerate deviations in the data, right? Problems in the data that might be hard to see, right? In a simple hyperbolic fit like this, you transform with one of these linear transforms, the deviations can become really clear, and that's when you kind of know, oh, something's not right, right? Because the ability of the data to fit this linear transform, it sort of requires that data be closely adhere to the model, right? Okay, so that's one good reason to do it. There's another good reason for using these linear transforms, and it has to do with when we start talking about different types of enzymatic mechanisms that can be distinguished using steady state kinetics. Turns out steady state kinetics is less powerful for this than other types of analysis, but it still has some utility. And we start talking about enzyme inhibition. These linear transforms can still be very useful there in terms of sort of visually demonstrating the existence of certain types of behavior, right? All right, so it's worth knowing about some of these linear transforms. And of course, the one you may have heard of before, and probably the most famous of these linear transforms, is of course linear transforms of the Michaelis-Menten equation, is of course the Lineweaver-Burk plot. Or sometimes also known as the double reciprocal plot. And the reason it's called this is because, well, first, the first guys who came up with the idea, Lineweaver and Burk, and then because fundamentally it's a double reciprocal of the basic Michaelis-Menten equation that transforms it into a linear dependence of the initial rate on the substrate concentration in double reciprocal space, right? So if you take the Michaelis-Menten equation, right, and we just invert it, so we go 1 over V naught would then just equal, of course, Km plus concentration of S divided by concentration of E0. Well, let's just stay. Let's make it simpler. Over V max, right, times the concentration of S, right? You split that up a little bit, what you realize is that, well, that means that 1 over V naught has to just be equal, if I sort of spread those terms out, to Km over V max, right, times 1 over concentration of S plus 1 over the V max, right? That's kind of cool, right? Because that looks a lot like Y equals mx plus b, right? Nice simple line, right? And this is great, right? So you can now take that same initial rate data, plot the inverse of the initial rate versus the inverse of the substrate concentration. And out of that, you get one of these nice double reciprocal Lineweaver-Burk plots. Looks something like this. And usually people are going to set these up where, oh shoot, you sort of, you'll see why if you don't remember your sort of zero crossing point for your X and Y axis is you sort of inset it just a bit here. And your data then would look something like this. You'd have data that go here. Right? And this data, again, if it's good steady state kinetic data, everything went well, fits the model well, you then get data that does something like this, which is fantastic, right? If everything works out this way. There are a couple of problems though. One is that if you look at how those points are distributed, you notice something, right? So remember, this is 1 over V naught, and this is 1 over concentration of substrate. So this is an inevitable consequence of what happens in double reciprocal space. When you do this to the Lineweaver, you do this to the Michaelis-Menten equation, your data points at high substrate concentration, remember, it's 1 over S, so your high substrate down here are compressed right down close to each other. And then your concentrations where you take measurements at much lower substrate concentrations then spread out, right, further down the plot. And they're not evenly distributed along this reciprocal axis. right? They can't be. And the consequence of that has to do with the fact that you look at where those points are arranged, and you also consider that at low substrate concentration, usually that's where you have your worst error bars, right? That's usually where your error bars are at their worst, right? And at high substrate concentrations, this is usually where you get the most robust signal, right, in your assay, and your data values are most well determined. So here's the problem. You take data like that, and you now want to fit a line to it. Within the variance of your data points, you now have lots of lines you could, in theory, fit to that data, right? So the problem is that trying to extract robust kinetic parameters from the Lineweaver-Burk plot is much less reliable than a direct fit or some of the other plots. I'll show you another one in a second. Because of the way in which the linear fit overweights the most poorly determined data points in the data set when you fit a line to those data points. The best determined data points have much less power in the linear regression than these other data points because of the spread down this axis, but they're also the most poorly determined, right? So it overemphasizes those data points, which makes it a problem. And so even in the era when people did lots of this fitting this way, in the graph paper era, the Lineweaver-Burk plot as a quantitative approach to extracting kinetic data was already sort of, or had fallen, or was already fallen out of favor. And people came up with lots of other ones, right? There are a whole variety of these different ones. If you read in some of the old enzyme literature, you'll see a whole bunch of these. One of the ones that was probably the best, or one of the best, was the so-called Eadie-Haastey plot. And you may see this one, right? And in this case, the linear transform involved turning the Michaelis-Menten equation into something that looked like this, where the initial rate equaled the Vmax minus the Km times the initial rate divided by the substrate concentration. So you can imagine some algebraic manipulation it took to rearrange the Michaelis-Menten equation into something that looked like that. Again, with the goal of turning this into a y equals, mx, plus b type equation, right? All right. So the good thing about the Eadie-Haastey plot is when you plot the data out, again, now you're going to be plotting initial rate over initial rate divided by the substrate concentration. You end up with a line of negative slope. It's linear again, but in this case, your data points are not overweighted. They're evenly distributed across that spot, across this space, which means you can now you could, in principle, extract a more reliable fit to your data, where now, of course, your intercept here is equal to the Vmax, right? And in this case, the slope is equal to minus Km, right? And your intercept here is now equal to Vmax over the Km, right? And I don't think I mentioned it, but similar sort of analysis of the Lineweaver-Burk plot allows you to get from these, like I said, from the slopes and intercepts, similar sorts of information, right? So in this case, for the Lineweaver-Burk plot, the slope, of course, of your fit is, of course, your Km over your Vmax, right? Right. While your intercept here, this is the reason for the false axis here. You have to do an extrapolation with the Lineweaver-Burk plot to get one of your intercepts. Your intercept to your zero crossing point of your y-axis with the x-axis, this, of course, is 1 over your Vmax, right? But to get the Km, if you want to get it directly, you have to extrapolate this plot back. Oops, that's not a very good line, is it? You have to extrapolate this plot back in order to get the intercept here, which is of course minus 1 over the km. Okay, again, present these plots mainly because they still will crop up. If you're reading older literature, you see them a lot. So you sort of need to know what they are and why they're there. Most people doing quantitative enzyme kinetics nowadays are not going to extract parameters this way. You're going to use a much more modern and more robust data fitting approach. But these linear transforms can still be, like I said, useful for demonstrating that your data really does visually adhere to a steady state kinetic model. All right, so we'll stop there.